So let me just say again for the recording that this is the overview of the lecture. We will talk about the general aspect of the interaction potential between the neutron and the electron spin. Then we talk about magnetic neutron diffraction. We talk about techniques for polarizing neutrons, and we'll give a little example from the field of frustrated magnetism, and it relates to this beautiful little image that you see at the bottom of the screen. Okay, all right, so first some rather basic things, and I have to say that I'm already noticing that there are some interesting little discrepancies in the formulas on this PowerPoint page. This has to do with something with the fonts, and I'm going to just charge ahead, and we'll see if we can't abstract for those oddities. Here's an oddity, and here's an oddity. I apologize for that. There is another way I can do it if it turns out to be too much of a problem, but then I won't be able to point. So let me try and just proceed the way it is. And so the first statement is that the neutron has a dipole moment. We mentioned that actually. Previously. And in this expression, I'm writing the dipole moment for the neutron, which is actually oriented in opposite direction of the angular momentum vector. This is not, that is not particularly important, one could say, but actually when you do set up your experiments, there are situations where you'd like to know that. But most of the time, this minus sign doesn't bother us too much. Here's the gyromagnetic ratio, 1.97 for the neutron. The Bohr magneton, 9.24 times 10 to the minus 27 joule per Tesla, and the ratio of the electron mass to the neutron mass. And this is the Dirac matrix, the Pauli matrix, and this is this blemish over here, and I apologize for that. So this is the Pauli matrix is sitting there. Okay, now the dipole moment for the neutron is 960 times smaller than the electron dipole moment, and this ratio is essentially the ratio of the neutron mass to the electron mass, the neutron being much heavier. Correspondingly, its magnetic dipole moment is much smaller, and there is, of course, the gyromagnetic ratio that shows up as well, which we couldn't have predicted its particular value. But so there is a magnetic dipole moment, but it's almost 1,000 times less than the dipole moment of the electron. And as you know, a dipole moment in a magnetic field has potential energy, and this is what it looks like. There's a dot product between the dipole moment operator and the magnetic B field, and this interaction potential will have the effect of essentially driving the neutron towards regions where the field is high, and it'll also want to align the neutron, or there will be a tendency for the neutron to align parallel to that magnetic field direction. And this is expressed in these two equations, that the torque exerted is the dipole moment crossed with the B field, and the force exerted is the gradient of the dot product between the dipole moment and the B field. So actually, for a uniform field, completely just a constant uniform field, there's not much of an effect at all, except at the boundaries towards entering that, and we will discuss that in a little. But what we do detect in the interaction of the neutron with the magnetic field distribution are actually gradients in the field, and so that will be borne out in the following. So those are just general things that you know from electromagnetism. And here I'm beginning to see some rather severe issues, and so I think I'm actually going to have to, and I apologize for that, I'm going to have to switch to another way of sharing this, in which you may not be able to see my little arrow. That's what it is, but we need to have a little better fonts here. So let me just see my arrow. Excellent. Okay. Okay. So we're back, and we apologize for the little glitch. This is the page that we already looked at. Now I'm going to talk about the transition matrix element. So we have the potential of interaction, and we're now going to basically develop an appropriate form for the interaction potential that we can then put into the formulas that we have for the scattering cross-section. And ultimately, what I'd like to see is an expression that involves the dipole-dipole interaction between the neutron spin and the electron spin. And so what I'm going to do is that I will develop an expression for the magnetic field generated by an electron spin, and then I will put that B field into the expression for the interaction between the neutron dipole moment and the electromagnetic field. So it's just a normal way of developing the expression for the dipole-dipole interaction. So on this first line, which I'm pointing to now, you see the normal expression within the parentheses for the vector potential associated with the spin operator S. You see it falls off as 1 over r squared. I take the curl of the vector potential to produce the B field. So this is simply an expression that relates the spin angular momentum to the corresponding B field as a function of my position coordinate. And eventually, as I go forward, this spin angular momentum vector is going to end up being an operator. The first step is then that I write down the interaction potential, which, as we said, was minus dipole moment of the neutron dotted with the B field generated by that electron. And I just simply put in the various, we have the various prefactors that come out in front. And you'll notice that there's a Bohr magneton squared that shows up. And that's because I have both a Bohr magneton that comes about due to the dipole moment of the electron. But in my expression for the dipole moment of the neutron, I also used the electronic Bohr magneton. And then it was modulated, or scaled, if you will, by the ratio of the electron to neutron mass. So that's what shows up there. So these are the various prefactors that appear. And then the core of it is this curl of the cross product of S dot R. Good. So then the transition matrix element that's going to show up in our scattering cross-section is written down here. And I think you can probably remember that what showed up in our scattering cross-section was this matrix element of the interaction potential between an initial state of neutron and actually also neutron spin state and the sample. So lambda is a variable which indicates the state of the sample, the initial state of the sample. And as you know, eventually I get to do a thermal average of all possible initial states weighted according to the thermal occupation factor. And then I have a final state for the neutron linear momentum and for its spin index and for the state of the sample. And these I will eventually sum over L prime, but I'm going to be looking at scattering into some specific solid angle of K prime states. And I have this interesting prefactor that shows up so that this whole term actually has a dimension of length. So now I put into that this particular form of the interaction potential. And then a step occurs which I'm not actually doing, which I'm not specifically doing here, which is that I'm calculating the matrix element between the plane wave state of the incident neutron and the scattered neutron. So this becomes a real space integration involving a plane wave. And this plane wave has an argument which is momentum transfer q dot r. And so that integral gets carried out. And what shows up then is this function f of q. And I'm going to mention that a little bit in my next step. And that actually will end up being what we call the magnetic form factor. And its extent in momentum space is actually a measure of the spatial extent of the spin density. So that's essentially most of what gets left from this, from calculating the matrix element involving the plane wave state of the neutrons. However, don't forget also this phase factor, which is very important. That one is accounting for the displacement of that spin away from the origin. So had I been exactly at the origin, then I wouldn't have that. Then I wouldn't have this this factor showing up. But I have that factor showing up because I want to describe the interaction or the transition matrix element associated with an electron which is sitting localized at this location RL. Now, some of you might begin to say, well, that sounds very weird that he's keeping track of the exact location of the electron and so on. But what I'm actually sort of making my way towards is the description of an electron which is bound at an atom, which is sitting at site RL in my material. So this is where this RL is going to come up. That's going to be the place at which this electron is bound. And F of Q is going to be the Fourier transform of the spin density associated with that bound electron. Good, but I still haven't summed over the initial and final neutron spin state. And most of what I'll be doing today, I'll be talking about unpolarized neutrons. So I typically will not know what the incident spin state of the neutron is, and also I will not be selecting in my scattering process. I would not be selecting the final spin state of the neutron either. So I'll end up doing a summation over both of those things. Now, the first thing I want to do is to talk a little bit about the strength of the magnetic scattering cross-section. And that actually comes out in this expression, in this prefactor R0. And R0 comes out, and this is probably healthy for you to do by collecting all of these various fundamental constants. Then that produces this R0 factor. And it's written down here. It becomes our measure of the strength of a magnetic scattering. And just in terms of which fundamental constants actually show up, they're shown here. It's the gyromagnetic ratio of the neutron, and that's natural because that comes in as a prefactor that determines in units of the angular momentum of the neutron how large the corresponding dipole moment is. So if gamma was to vanish, well, then I wouldn't have any dipole moment at all. So certainly the strength of scattering will scale with that. And then this other factor that shows up is this so-called classical electron radius. And so that's in some sort of semi-classical description of the electron, a measure of its size, if you will. But we won't get into that. But we will get into what the actual value for this constant R0 is. It turns out to be 0.54 times 10 to the minus 12 centimeters. And this is, it is what it is, but it's important for our experiment because this number is actually quite similar to the bound coherent scattering length for many nuclei. So not identical, but in order of magnitude, it is just about the same number. And that means that the strength of magnetic scattering is going to be quite similar to the strength of scattering associated with a strong nuclear force. And this is important because it means that when we do neutron scattering experiments on magnetic materials, we'll find that the magnetic scattering intensities will be roughly as strong as the nuclear scattering intensities. And so we will see Bragg scattering that is associated with strong nuclear force and the locations of the nuclei. And we'll also see Bragg scattering that has to do with the orientation of the magnetic dipole moments of the electrons that are presenting an unpaired, that are in the partially filled shells. So these partially filled shells will generate magnetic dipole moments, which generate fields, which give rise to scattering. And what I'm saying is that the strength of that scattering is pretty similar to the scattering associated with the nuclei. And this is quite different, actually, from the case of X-rays. As you know, normally we associate with X-ray scattering measurement of the charge density and that's sort of how we consider X-rays as coupling two materials. But there are also magnetic parts to those scattering cross-sections. This is beyond what we're talking about in this course. But in the case of X-rays, these are very, very weak cross-sections compared to the charge scattering cross-sections. Doesn't mean it's not a very useful and very powerful technique, but it's quite marked that in neutron scattering experiments, these magnetic cross-sections are really very pronounced and will be very noticeable as soon as you put a material in the beam which has magnetic properties. You will begin to see scattering associated with that. Okay, now there's an important additional feature I want to mention already here, and we're going to see it throughout our discussions. And that is that when I take the Fourier transform of this curl of a cross product, then essentially what what happens is that this curl operator ends up becoming like a momentum transfer operator. It becomes like a Q cross. And as a result of that, in this transition matrix element, we find that we are sensitive only to what we call the transverse component of the dipole moment. Let me specify that a bit more. What I mean with transverse, I mean transverse to momentum transfer. So that spin density or dipole moments which are aligned in parallel to my momentum transfer of the scattering process, those actually will not give rise to magnetic scattering. So I have sort of a blind eye for any magnetization which is pointing in the direction of momentum transfer. And this is a result of the nature of this of the Fourier transform of this expression. So if you will, a result of the particular form of the dipole-dipole interaction will actually cancel out that part, that particular aspect of the cross section. And this is actually turns out to be some form of a blessing, or it's actually quite convenient in a sense that it's possible to get some information about the orientation of magnetic dipole moments in materials by looking at this so-called polarization factor. And I'm going to be returning to that a couple of times through the lecture. And this is emphasized in the formula at the bottom of the page, that it is this S perpendicular component of the angular momentum operator that we're actually sensitive to. And this can be written out in this form. Here's the full vector. And here I'm subtracting out, I think these should have been unit vectors, but I'm subtracting out the component of S, which is parallel to Q, because I don't actually see that one at all. And so in the case where SL is completely parallel to Q, well, then this one actually vanishes completely. And so we'll return to that a couple of times going forward. Okay, let me just ask if there are any questions at this point. If you do have questions, please just type them into the chat window, and my my trusted assistant over here will soon alert me to it. So right now I'm not actually seeing your questions directly, but please, anything you have you'd like to ask, or if you'd like to comment, we should go slower or faster, we can do that. But not seeing any questions right now, let me proceed. And what I'd like to do now is have a little digression before we return to the discussion of the scattering cross-section. And in this digression, I am making a connection between the nuclear and the magnetic scattering part. And what I'm writing down here is the interaction potential. And this is now the interaction potential that of the form that we've been discussing when we talked about neutron optics. Remember, we introduced the Fermi-Soda potential, which was this very spiky function that had a delta function at the location of each nucleus. And then we said that if we were in a situation where interference effects were not important, and then we discussed how one could get into that limit, then we could think about the neutron-nuclear interaction as a smeared potential, which would not know about, if you will, the features that were occurring at the atomic scale. And this gave rise to this sort of smeared nuclear potential, which is what I have in the first part of this expression. So 2 pi h bar squared over m times the density of nuclei times the bound coherent scattering length. This is this typically positive potential that is associated with a neutron entering a material. So what I've added or subtracted as the case might be, actually I think the way I've written it, I wouldn't need the plus or minus. I can just have a plus there, actually. What I have there is the corresponding potential associated with the dipole-dipole interaction between the neutron and the magnetization in the sample. And so now, you remember when we talked about the smeared nuclear potential, I said that it was akin to a electromagnetic description where we are always averaging typically over some appropriate length scale. And likewise, when we talk about the dipole-dipole interaction, now I'm not going to be concerned about the particular distribution of dipole moments from side to side in the sample, but I'm going to talk about a smeared dipole moment distribution. And of course, the appropriate description of that is in terms of the magnetization density. So this is m vector is the dipole moment per volume unit. And so this expression for the magnetic part of the interaction is simply the expression for the energy of a neutron in the magnetization of the material, but it also actually follows from the previous expressions that we were writing down. So that is the interaction potential in the optic limit for the nuclear part and the magnetic part. And you might remember that when we previously talked about just the nuclear part, we related that to an index of refraction. And the index of refraction was this square root of 1 minus the value of the potential divided by the energy. And the interesting part that occurs, just remind you of that in the case of neutron optics, is that the index of refraction is actually less than 1. When in optics, we are familiar with the index of refraction being greater than 1, so that the speed of light inside dense materials is less than the speed of light in vacuum. But here's actually, it's actually opposite, so the index of refraction is less than 1. And this is interesting and important because that means that in Snell's law, we end up being able to have total reflection take place when we go from a vacuum to a material. And we talked about that in the case of the nuclear interaction, that we could have this kind of glancing total external reflection take place. And by writing the expression, by introducing the expression for V into this square root, I end up with this type of expression for the index of refraction. And the interesting thing here is that the index of refraction is going to depend on the spin state of the sample. So if the spin is parallel to the magnetization, and here I shouldn't have had both a plus and minus. Let's say that it's let's just use the plus here. When I'm parallel to the magnetization, then I would actually have a more positive number here and therefore a smaller index of refraction. If I'm anti-parallel, this term will end up subtracting, and then I'll have a smaller number in the parentheses, and I'll have actually a larger index of refraction. So in other words, the index of refraction is going to depend on the spin projection onto the magnetization of the material. And this is quite interesting because it then becomes a means of actually selecting the spin state of the neutron beam. So imagine that I have an initially unpolarized neutron beam and I would like to polarize it. Then this is actually a way that I can do that. I can use total external reflection. And just to show you this little image down here that relates that, the critical angle for total external reflection is given in this expression, and you can see that it'll be different for the different projections of spin onto magnetization density. So you can imagine coming in at an angle which is close to the angle for total external reflection, and then depending on whether I am parallel, as was the case here, or anti-parallel to the magnetization in the sample, then I will either be able to reflect in a total external reflection, or I'll be able to refract in the case when I'm anti-parallel to the magnetization. And so if I was to then set up a situation in which I only receive the reflected beam, for example, then I would have gone from an unpolarized neutron beam to a polarized neutron beam. This is one of the ways that that is employed to actually polarize neutrons, simply relying on the potential of the neutron inside the magnetized material. Now, one thing I want to just point out here is that wave vector transfer in this scattering process is along this direction indicated. This blue vector Q indicates wave vector transfer. You remember wave vector transfer is k minus k prime, so that's a vector pointing down in that direction. And if I was to orient the magnetization density parallel to that direction, then in this particular configuration, I wouldn't actually have a distinction in the critical angle, and I would not be able to polarize the beam in that case. And so you notice here an example in which this situation where the magnetization is perpendicular to Q, that's the situation in which we have an effect from the magnetism on the scattering cross-section. So I just wanted to point it out also in that case. So this was all the Newton optics limit, in which we have no sort of spatial interference phenomena, and we are thinking about variations in the potentials over semi-macroscopic length scales. But now I want to come back to talk about the actual diffraction processes. And so I pick up again the expression for the scattering cross-section. And I'm actually going to talk about the partial differential scattering cross-section, which is indicated here. And this whole expression you saw previously, we had a ratio of neutron velocities. We had this this famous factor that shows up in the transition matrix element, and then we have finally energy conservation implemented in the Dirac delta function. So let's not repeat how we arrived at that expression, but I simply put in as my transition matrix element this dipole-dipole interaction that we derived a couple of pages back. And so that's what's happened on the next line. And let's just walk you through that expression. First, remind you that the overall strength of it is going to be proportional to the essentially the classical electron radius squared. And then there's this term, which is the magnetic form factor, which, as we said, and that's actually written up here, is the Fourier transform of the spin density. There is also the G factor associated with the bound state formed by this electron, which would be 2 for a free electron, but it could be something else. If I'm talking about for example, a rare earth or transition metal ion, I could end up with a different G factor appearing. Just conceptually, the G factor essentially has to show up squared, because what we, after all, are scattering from is the magnetic dipole moment, and it grows in proportion to G, so it's expected that we should have this G squared show up. Okay, then comes the Debye-Waller factor, and this comes in because there is still going to be vibrational motion of the atom about which this electron, which forms a dipole moment, is bound. And this vibration will further smear the dipole-dipole interaction potential in such a way that I will be suppressing the scattering at large momentum transfer in accordance with this Debye-Waller factor. And then come the two Fourier transform, the time Fourier transform, which you recall showed up as a result of this Dirac delta function. And then comes the spatial Fourier transform, LL prime e to the I Q L RL minus RL prime. And then finally comes essentially the 2-point correlation function. And now one thing that this expression involves both a thermal average, which is the outer parentheses, but also there's still a matrix element that involves the spin state of the neutron, the initial spin state and the final spin state of the neutron. And if we have an unspecified incident and final neutron spin state, then I get to actually average over those things. So this would be sort of the specified cross-section, but if I don't know about the incident neutron spin or the scattered spin state, then I get to sum, and this is then what I end up measuring. And once I carry out that summation, I end up with this expression for the unpolarized magnetic neutron scattering cross-section. And I want to just point out the various terms. Again, the Debye-Waller factor, I mentioned that. The spin correlation function down here is almost the most important part of the entire expression. And you remember that I've always said that we're measuring a 2-point correlation function in time and space. And here you see indeed these two positions in space, L and L prime, show up. And I'm sensitive to the thermal expectation value of a component of the spin operator at that site and at this time of 0 relative to the another component of the spin operator at a different site and at a different time. So this is the nature of a 2-point correlation function. And as I said, I get to Fourier transform that one in both in time and in space. This factor up here let me just, I think I've got other pointers here. This factor up here is the so-called polarization factor, and it is simply implementing this statement that I mentioned previously, that we always measure the dipole moment density, which is perpendicular to wave vector transfer. So that is, there you have it in all its glory, the magnetic partial differential scattering cross-section. And I don't know if there are any questions at this point, or whether you're completely stunned. No questions. So please feel free to ask any questions you might have. Now I'm going to, okay, I have one thing I just want to mention first, and that is that in writing down this expression, and I sort of went a little faster than normal through the calculation. In writing it down, I have, in a sense, decoupled the vibrational motion of the atoms that carry the dipole moment from the magnetic properties. I did include the Debye-Waller factor, but when I do my summation over positions in the lattice, I'm summing over the thermal equilibrium positions of those atoms. And I'm not thinking about sort of mixed magnetic and vibrational excitations. So this is sort of a way that we try to simplify matters. And you'll see that reflected in much of what we do, is that when we are focusing on the magnetic cross-section, then we really try to move away the other complexities. So I don't want to see the phonons show up in this expression, even though experimentally I should be aware of the possibility of those types of things as well. So now I'm going to, actually throughout this lecture, I'm going to focus entirely on diffraction part of this scattering cross-section. And then in the next lecture on Thursday, we're going to pick up and talk about magnetic excitations. But if I talk about the elastic part of the scattering, then in this two-point correlation function that I emphasized, I'm going to be thinking about the long time limit of it. Remember, I had SL at time 0 and SL prime at time t. Well, I'm going to think about that thermal average in the limit where time has gone to infinite. Of course, if I have some sort of a paramagnetic state or some sort of a spin liquid state that we'll be talking about later, then this correlation function may not have a finite value when time goes to infinite. It may actually vanish when time goes to infinite. In fact, most materials which are not sort of magnetically ordered would not have a finite limit to that two-point correlation function in the time goes to infinite limit. And so at this point, if I want to see magnetic diffraction, I need to be looking for materials that, in fact, have some form of static magnetic ordering. And so that's what I'll be talking about here. So as I mentioned here, if there are time-independent spin correlations, then I will have elastic scattering. And the corresponding expression is then written below, and it ends up being simply a spatial Fourier transform of that spin configuration. You see, I've now lost the time indexes on these because I'm just looking at their time averaged values. And so you could say that the now diffraction cross-section is simply a measure of the spatial Fourier transform of the spin configuration. That's what I'm measuring in my diffraction. Not, a big surprise, since that's sort of similar to the story that we have when we talk about diffracting from the nuclei. So now if I have a periodic magnetic structure, then I'm going to end up with magnetic Bragg peaks. And then I can further simplify this expression in this form. And you'll see that just like in the case of nuclear diffraction, I have a summation over all the reciprocal lattice vectors showing up. And I've indexed those tau m because these are the magnetic reciprocal lattice vectors. And the magnetic reciprocal lattice might be different than the nuclear reciprocal lattice, because I might have translational symmetry breaking, which will introduce additional Bragg peaks, as we'll actually see in a little. And so I got to sum over all of those magnetic reciprocal lattice points. I have this factor here, which is the number of magnetic unit cells, which might be different from the number of unit cells of the underlying structure, because I may have increased the size of the unit cell. And then here comes the structure factor in the case of magnetic scattering. Now, in the case of nuclear diffraction, this structure factor was essentially a Fourier transform within a unit cell of the arrangement of nuclei with each of their scattering lengths, BD. I think we had the expression on the board at some previous stage. In the case of magnetic scattering, the expression is actually a vector structure factor, and it's written here at the very bottom. And so here I actually have, if you will, a discrete Fourier transform. So I'm summing over all of the spins which are in the magnetic unit cell, and then I'm summing up the expectation value of the angular momentum vector, and it gets to be Fourier transformed according to this phase factor. There are various other things in there to decorate it, namely the form factor that we talked about previously, and it might be different from magnetic side to magnetic side. There's the Debye-Waller factor, which could be different as well. Things might vibrate in different amounts, and the G factor could be different. So essentially, the intensity of my magnetic Bragg peaks is going to be measured by essentially the strength of this vector structure factor. Now, of course, my diffraction cross-section is eventually a scalar, so I have to form from this vector a scalar, and the appropriate expression is written here, and it implements this thing that I was mentioning previously, that we're only sensitive to spin density, which is perpendicular to wave vector transfer. So once again, if all of the spins are pointing in some particular direction, then when wave vector transfer is also pointing along that direction, then this difference will actually vanish, and then I have no diffraction at all. And so this is sort of a pretty dominant feature in the cross-section. We call this, as I mentioned previously, a polarization effect or the polarization factor, and we use it when we try to determine the nature of these ordered magnetic structures. So there you have it. That's the magnetic neutron diffraction cross-section. Right? Are you you're getting it so far? Good. All right, so then let us now take a couple of specific examples. And the first example, there's a question? Okay, that's an excellent question. Excellent question. Does the previous formalism apply to itinerant magnetism? So I would say that operationally, essentially, it does, and this is because in describing the itinerant magnetism, we will typically adopt some form of a tight binding approximation or a tight binding description of the system, and then we'll end up having the atomic orbitals still being essentially what they were in the localized case. And so the fact that we're dealing instead with a system where the electrons are itinerant is actually tough to get a really strong experimental signature of that. It doesn't show up in this form factor very well, even though, conceptually you would expect it to eventually show up at sufficiently large, so I should say different, a sufficiently short momentum transfer, which corresponds to large distances in real space. I ought to see some sort of effect of the itineracy of those electrons. But to tell you the truth is that experimentally it's pretty difficult to pick that up in the form factor, because you end up being really dominated by the tendency of this the tendency of the dipole moment to actually be localized around the atoms within some sort of tight binding description. So this would hold both in the case of transition metal ions and certainly in the case of rare earth ions. So rare earth ions, the spin density is really quite well localized around the atom. And so even though you might be talking about some sort of maybe a heavy fermion system which has magnetic order, you'll eventually find that the form factor is pretty similar to that which you would associate just with the atomic spin density distribution. So we have to look elsewhere to make the distinction between an itinerant magnetism and really a localized magnetism. In the diffraction cross-section, it's pretty difficult to pick up. So typically we might need to look at the nature of the excitations, or we may need to look at the pressure dependence of the magnetism, other sort of more intricate experiments to really make a determination as to what is the appropriate way of thinking about that type of magnetism. But if you're simply looking at the Fourier transform of the dipole moment distribution in the ordered state of an itinerant magnet and in the ordered state of a localized magnet, it's quite difficult to distinguish those things. I think it's a very important thing to notice, because somehow theoretically the description looks totally different, but experimentally it's really almost indistinguishable, and it's not indistinguishable but almost. Does that more or less answer it? Okay. Good. So then we come back to this case, and I'm just going to gradually come to more complicated situations. And first, the ferromagnet. And here's sort of an interesting aspect of it, because normally we like to separate out the magnetic scattering from the nuclear scattering. But of course, in actuality, we have both of those types of interactions going on simultaneously. And so it's important you keep that in mind when you hear talks about magnetic neutron scattering and so on. You'll tend to find that the speaker focuses entirely on the magnetic scattering, but the nuclear scattering is still in there, and somehow they had to find a way of separating it out. And here I want to tell you about a case of a ferromagnet where it's particularly where there's a very close connection between the magnetic and the nuclear scattering. So I've written down basically the sum of the scattering length associated with the strong nuclear force and the scattering length, if you will, that's associated with the ordered dipole moment. So this is similar to what we did when we had the expression for the what's it called, the optical potential. We had an expression like that showing up. In my diffraction cross section, here the formalism is a little bit loose, I will admit, but in the diffraction cross section, we're going to be looking at essentially a Fourier transform of this scattering length, which has now a nuclear and a magnetic part over a unit cell. That will be my structure factor. And so this type of expression will show up in my scattering cross section. And if I take the modulus squared here, I'm going to get essentially three terms. One is entirely having to do with the nuclear interaction. One having to do with the magnetic interaction. Oops. Sorry. Oh, I apologize. I see I shouldn't have had the BD plus here. So that should have been, that's not good. So this BD plus should have not been there at all. So this one should have been just entirely magnetic. And then this guy here is the cross term, which has to do with the product of the magnetic and the nuclear part. And so in the case of, so this term here will give me my nuclear Bragg peaks. This will place additional magnetic intensity on top of my nuclear Bragg peaks. So again, forget this BD plus. So that will produce intensity on top of the nuclear Bragg peak, and then this term can actually add and subtract from that. But the interesting thing is that if I have an unpolarized incident neutron beam, then the sigma gets to be plus or minus. So this term actually will drop out. So in the case of an unpolarized beam, then I'm actually going to just end up getting the sum of the nuclear and the magnetic scattering parts. Those will just end up adding up like that. Now, in the case where there is, however, an important consequence of this, which is that the diffracted beam will actually end up being polarized. The strength of the scattering will be as if it is simply separate nuclear and magnetic scattering, but I'll end up actually producing a polarized beam from this scattering process. And you can see it if you just look at this expression itself. If I was to manage to match the magnitude of BD and sigma R0 SD, then I could actually manage to completely cancel this stuff out and make this thing actually go away. And so this can be used as another means of actually polarizing the beam. And there are certain crystals which manage to make these things become similar in magnitude, and then you can actually manage to have, for one spin state, you can have a finite value, and for the other spin state, you can have it actually vanish. Okay, all right. So then let me go on to talk about the case of a simple cubic antiferromagnet. And so this is one step up in complexity, if you will. And so here's my cube of spins, and I'm going to have each of the nearest neighbors be anti-parallel to each other. So this is a typical configuration. And I just want to show you what happens when I feed in this type of spin configuration into the expression for the scattering cross section. And so the vector structure factor now looks like this. And in my expression for the scattering cross section, because all of the spins are pointing in one particular direction, the z direction, then my vector does not have, it always is pointing in the z direction, the vector structure factor. And so as a result of that, the so-called polarization factor becomes very simple. It's just 1 minus the direction cosine along the z direction. And so you can see that if wave vector transfer is really along the z direction, then this parentheses will go away. And so this is telling me that, as I mentioned previously, that when the spin density is along momentum transfer, then there's no magnetic scattering at all. So all of the diffraction will simply go away when that happens. And you could say, well, that's not so good, but it's actually good because it allows you experimentally to determine the direction of the spins in such a antiferromagnetic structure or a ferromagnetic structure. Because when I find a direction where all of the magnetic scattering goes away, well, then I've found the direction of the ordered moment in that structure. Then I have the sum over the magnetic reciprocal lattice vectors. And here's an important point, which is that the unit cell has actually doubled in all three directions. It's doubled along the x, y, and z direction. And this is indicated over here that the chemical unit cell, if you will, is this. But because of the magnetic ordering, which has made the colors different from red to blue as I go from side to side, the new unit cell is actually 2 times 2 times 2 is 8 times as large as the previous one. And this means that I'm going to have also, I think, 8 times as many reciprocal lattice vectors in all directions, twice as many as I had previously. And so in my reciprocal space map, what I've shown you here in black are the locations of the nuclear Bragg peaks. And then what's shown in yellow are the locations of magnetic Bragg peaks. Now you might say, well, but he said I would have doubled the unit cell in all directions, and so I ought to have the new reciprocal lattice vectors be half of the previous ones, so that I would just have, I should also have a peak sitting, let's say, right at this black place, and I should also have a peak sitting at this location. And in fact, technically, those are also locations in the magnetic reciprocal lattice. However, the structure factor, which is listed up here, actually vanishes because it's only finite when h, let's see, what's the story here? When none of these HKL is an integer. When any of those is an integer, then you'll get sine to an integer times pi, which vanishes. So that will really kill the magnetic intensity at that point. And so therefore, it's only these places in the center of the old unit cells where I actually end up seeing magnetic scattering intensity appearing. And then, as I mentioned, this is my sketch down here, which is very important to keep in mind, is that I'm really only going to be seeing these Bragg peaks at all when my wave vector is not parallel to the z direction. So that was diffraction of a simple cubic antiferromagnetic structure. And then I want to go to a slightly less simple case of a so-called Heli-magnet. And so this is the case of manganese O2. And so there you have a situation, and I won't really be able to describe it in sort of full detail, but I want to bring out a certain feature of that. And then I'm going to pose a homework problem where you can work through some of this yourself. That will come on Thursday. So the spin configuration is such that as I come along the c direction, the dipole moment appears to be rotating. So from plane to plane, it rotates as indicated here. Now that type of spin configuration can be described by this expression. So it looks like some sort of circular polarized light or something like that. That's just a mathematical form. If you evaluate this expression, it will generate this type of if I take the think I need to. Ooh, everything's okay. Yeah, I think everything is okay. This factor here is actually implementing the way that the phase changes for this spiraling configuration when I move between different sides of this Bravais lattice with a basis. So that's why I need this factor to show up as well. And you'll get to explore and enjoy that in the homework problem. But fundamentally, it's this cosine term in quadrature which is producing the spiraling spin configuration. And so what you have to do is to put this now into this Fourier transform, which is the magnetic diffraction cross section. And when you do that, you end up with the expression which is listed down here. I just want to call out a couple of interesting features in that. And I think the most interesting feature is that I get reciprocal. I get a sum here which is over. Actually, this is reciprocal lattice vectors of the chemical unit cell. And then displaced away from those, I get what we call magnetic satellites. And you'll see that QM appears in the expression. Now, what was QM? That was the wave vector that was associated with this spiraling spin configuration. So it showed up in our expression for the spin configuration. So it's, in a sense, pretty natural that because the expression for the spin involves a specific wave vector, when I carry out this spatial Fourier transform, I see that wave vector appearing in the sequence of delta functions, and it functions in a way as a carrier wave on top of the Bragg peaks of the chemical unit cell. I have this additional modulation which then produces these side bands or magnetic diffraction satellites, as we typically call them. And so actually by looking at the location of these satellites with respect to the nuclear Bragg peaks, we get to know something about the pitch of the spiral. If these peaks are very, very close to the nuclear Bragg peaks, then it'll be a very, very long wavelength spiral, and if they're somewhere in between, the wavelength is much shorter. So that's what these two terms do. The other thing I wanted to point out is this term, that is the polarization factor. And you'll see that as opposed to the previous case, which was a uniaxial spin configuration, where all the spins were in a certain direction, here it's a planar spin configuration. And you actually gain in intensity when you have a larger direction cosine along the direction of C that is perpendicular to the spiral. Now you can see what's happening is that as I mentioned, it's always the projection of the spin density onto the normal plane to wave vector transfer. And this projection becomes larger and larger as my wave vector transfer is oriented more and more along the C direction. So those are the key features. I guess one other feature to mention is that the overall intensity involved has to do with the magnitude of the moment associated with the spiral S. It comes in squared, and then I have this the famous R0 factor that we mentioned from the beginning, which measures the overall strength of magnetic scattering. Now, of course, I'd like to emphasize that what you typically do in the experiment is that you don't know this expression as you come in. What you do is you carry out the measurement, and you find these peaks sitting in strange places in momentum in the wave vector space, and then you try to figure out the systematics of that, and then you from that you figure out what the spiral actually looks like. So you're sort of always operating in the opposite sense. We don't know what the spin configuration is yet, but we look at the data and then we try to back it out by knowledge of these types of cross sections. So that was the Heli-magnet, and let's see. I wanted to point out that not all magnetic structures are periodic structures. And in fact, some of the structures that we're more interested in nowadays are specifically not periodic. That's the case for something called spin ice. I just wanted to briefly mention that. At this conference I'm at, there's a lot of discussion about those types of materials. Here's an example of such a material. It's holmium-2 titanium-207. And I don't think I can go into too much detail about it. I just want to, from the perspective of carrying out the experiment, what is found when you do the diffraction experiments is not magnetic Bragg peaks, as we had talked about in the previous examples. There are no sharp features. There are no like sharp delta function features at all found in the magnetic diffraction. There is elastic scattering, but it's not collected in these sharp Dirac delta functions. And so experimentally, in a sense, when you see these broad features, and what I'm showing you here is the intensity as a function of momentum transfer, and when you see these very, very broad features in momentum space, that immediately should tell you that now you're dealing with a system which is not periodic in real space, because the Fourier transform as seen in diffraction is not discrete anymore. So there's some sort of aperiodic aspect to this system. On the other hand, there's some very, very sharp features in the pattern, and this is what's indicated here as pinch points. And there, if you vary momentum transfer in this direction across a pinch point, you'll find a very, very sharp ridge of intensity. And that's actually saying that there is a very long length scale involved also in this spin structure. Even though it's not a periodic spin structure, it's not a completely disordered spin structure, because there's some aspect of it which produces this very sharp feature in momentum space, and something sharp in momentum space is something very, very large in real space. And it turns out that the length scale that becomes very large for these spin ice systems is actually the distance between tetrahedra. Here's one tetrahedron. It's the distance between tetrahedra which do not have two spins in and two spins out. So, by far the preponderance of the tetrahedra in the structure at low temperatures, they always have two spins in and two spins pointing out. But it turns out that in this particular structure of corner-sharing tetrahedra, there are many, many ways you can do that. And so you don't end up with a periodic structure, even though you have that strong constraint of two spins in, two spins out. However, the strong constraint leads to a very long distance between locations which violate that constraint. And this long distance is what gives rise to those sharp features in the diffraction pattern. So this is just the interpretation of these diffraction patterns can become a lot more interesting, if you will, when we're thinking about structures which have aperiodic aspects to them. When we're thinking about periodic structures, on the other hand, we're back essentially to the type of crystallography that you do also when you're trying to solve the chemical structure. It's sort of a decoration on top of that, resulting from the dipole moments when we have these periodic structures. Okay, all right. So are there any questions now? No questions. Okay. So then I'm going to give you one other example. We've got about 10 minutes left, and I have one more example from recent experiments, and this is also sort of to take you into the process that often is involved when we're trying to understand magnetic structures based on observed diffraction patterns. I want to sort of emphasize that we always, when we're doing research, we're going the other way around. We see something that we don't understand in the diffraction pattern, and then we try to figure out what that means in real space. And this example I want to talk about involves the case of nickel gallium-2 sulfur 4. And I can't really sort of talk in detail about the physics of that, but I just want to pull out a couple of specific points. If you're interested in more in this subject, you can read the paper which came out in Science in 2005. First author is Nakatsuji. The thing I want to mention is that it's a very planar structure. So you have these blocks, essentially, or these very large planes of nickel atoms, which are very well separated from their neighboring planes. They're separated very well magnetically because the crystal is actually only tied together, if you will, by a so-called van der Waals effect. So you can almost, if you have this crystal, you can sort of just pull it apart, pull these planes apart. It's a very, very loosely attached structure. And this is quite interesting because it makes the magnetism what we call quasi-two-dimensional. And it turns out that magnetism in 2 dimensions is very delicate. The quantum fluctuations can become strong enough to completely suppress the occurrence of a real long-range ordered spin configuration. And so there's quite a lot of interest in these types of systems. Now, as often happens, and as often is the case, these types of new materials are not available initially in single crystalline form. And they're only available typically in the form of a powder sample. Now, a powder sample has the crystal oriented in all sorts of different fashions. And so you have a complete spherical average going on in your diffraction cross-section. And I wanted to just give you a word about what happens in that case. So we will measure then the so-called powder diffraction cross-section, which is a spherical average. Yeah, this is correct. So it's a spherical average of the crystal diffraction cross-section. And this spherical average is indicated here. I need to think about, so I establish in my laboratory a certain direction for momentum transfer, but the crystal is rotated in every sort of way, or every possible way with respect to that, because it is a powder sample. And so I don't get to see the detailed crystalline diffraction cross-section. I only get to see the spherical average. But the good news is that you can actually learn a lot from that, particularly when you're dealing with a low-dimensional structure. And here's actually an example of such a diffraction cross-section. And so this is magnetic diffraction. You see these interesting sort of modulated features. And these types of data, initially when you pick them up, you think, my God, that looks kind of rough and a little bit messy. But there's a lot of information that can be pulled out. The first and interesting point is that this initial edge here is very, very sharp. This step is very sharp. And this immediately, when you've done this for a little time, you know that when you see something which is sharp in momentum space, it means that you have some relatively long length scale involved in this material. So there's some sort of relatively long magnetic correlation length that is involved. On the other hand, there are also some very broad features that we see. We don't really see many other sharp features. Perhaps there's also some statistics involved here. So that means that there are also some very short length scales involved. And of course, as you might be able to guess, the short length scales have to do with the correlations between spins which are in neighboring planes. So basically, spins which are in each plane are sort of happy to deal just with their neighbors in that plane, and they don't really worry too much about what's happening in the next plane. Let me just do a little sketch on the board to give you a sense of that. What happens then is that I'm going to, just to give you a sense of a three-dimensional momentum space, I have Qx and Qy and Qz. And imagine that I have these planes of my two-dimensional magnets forming the Qx, Qy plane. Now, what happens in this case is that because there are no correlations in the z direction, there'll be no interference effects in the z direction. And so the entire diffraction cross-section will actually not depend on the z component of momentum transfer. That means that even though I have a relatively long correlation length in the Qx, Qy plane, I'm gonna not have any correlations in the z direction. In momentum space, what that means that I'm going to have, let me draw it here, I'm going to have some sort of relatively sharp feature in the Qx, Qy plane, but then this will be some rather long rod, essentially, of scattering in the z direction. So my diffraction cross-section, if I actually had a single crystal, would be in the form of sort of a tube of scattering. So instead of a sharp feature in momentum space, like a Dirac delta function, as we would have it in a three-dimensional crystal, and instead I have this sort of very, very oblong tube. And I've only drawn one of those tubes, but if I had a hexagonal crystal, I would have sort of 6 of those tubes typically, and then I might have some higher order tubes up here as well. Now, what happens when I'm dealing with a powder sample is that I'm going to be measuring not this beautiful pattern in the three-dimensional momentum space, but I'm going to have to average over a so-called eval sphere. So I'm going to always be measuring as I change my length of momentum transfer. As I change momentum transfer, imagine collecting the intensity which lands on this sphere. And so then what happens is that at small momentum transfer, and maybe you can keep an eye in your mind's eye about that little pattern of diffraction that I showed you. At small momentum transfer, this sphere does not intersect any of these rods. But then there'll be a certain momentum transfer, sort of a critical momentum transfer, where I just begin to hit this rod. And that is where I'm going to see the very sharp feature, the sharp feature being the small extent of the rod in the plane of the two-dimensional magnet. And then when I go beyond that to larger momentum transfer, then I'll be cutting through this rod. And in fact, I'll keep having this rod cut through my eval sphere, even as I go to larger and larger momentum transfer. And it's not until I meet the next tube, which might lie out at some greater value momentum transfer, then I might see a sharp feature in the pattern again. And so this gives rise typically to this, I just draw up here, the result of this will be intensity as a function of now scalar Q, because when I'm talking about a powder sample, I only have the scalar Q. What I'm going to see is intensity, which is initially no intensity because I'm in here. Then I hit the edge, and I get some sort of sharp onset, and then I get some sort of decrease in intensity as I walk out along that direction. And all of this is completely quantitative, so that if I have a specific model for the diffraction in this three-dimensional space, then I can take a spherical average and predict what it should look like as I scatter from a powder. And I just want to show you, I think I'm sort of running out of time, but I'm just going to show you in the case, let's see if I can get myself back to speed here. I see. Okay, I hope we won't. I hope we'll be able to get that to work. Let's see. I think it's okay. Okay. Let's see. Oh, there we go. There we go. So it seems to take a little time. So this red line that you see drawn through the data, that was actually calculated for a certain model for the diffraction cross-section in the crystal. So I just carried out the spherical average and generated this red line. So it's a very, very highly constrained fit to the data, which actually works out quite nicely, and which gave a lot of conclusions regarding the magnetism in that system. And eventually, when we obtained, as shown in the next graph, and you can look at this offline after the lecture if you're interested, when we eventually obtained single crystalline samples, then we were able to carry out the diffraction experiment. And let's see, somehow it doesn't seem to be. I don't seem to be seeing it being transmitted to you, but perhaps I'm not sure if you can. Oh, you might just have lost your connection, but others might be okay. So let me just. So this picture actually now shows the diffraction cross section as measured once we had crystals, and so there you can see in the plane of the two-dimensional magnet, we actually see well-defined peaks, which are actually the intersection of these, which is in a sense looking at these tubes from above. We see those features, and so in fact, the results which were inferred from the powder diffraction measurements were completely borne out later when we carried out diffraction experiments on single crystals once they became available. So there you have it. Just to finally summarize, though I'm not certain whether you're seeing this slide, but let me just summarize what we've yeah, I think now you're seeing some of the slides for the diffraction from a single crystal. And then as a summary, I just want to say that the neutron, just to summarize what we did, the neutron has a small dipole moment, and it can scatter then from the magnetic fields generated by electrons, particularly in partially filled orbitals. The magnetic scattering is similar in magnitude to nuclear scattering. The elastic magnetic scattering probes static magnetic structure. The spin direction gleaned from polarization factor. You remember what I emphasized several times, that we see the projection of spin density onto the normal plane to momentum transfer. Periodic structures are determined by looking at Bragg intensities, and they're revealed to be periodic by the appearance of Bragg intensities. But we can also learn a lot about more interesting short-range ordered magnetic structures by exercising our abilities to think about the Fourier transform. And I also talked a little bit about how to analyze data from powder samples. And with that, we have finished our discussions of magnetic diffraction. And as I mentioned, I'll get some homework problems to you to think about this in greater detail on Thursday. Okay, thank you very much. Thank you very much for joining. Good afternoon.